We've talked quite a bit about delta and Y connections in some of our other videos, and we thought it would be important to outline some of the physical attributes of these sorts of connections in a video. You see, in the PE, you'll not only need to know the more abstract and mathematical elements and issues regarding delta and Y connections, you should also know something about the actual physical connections as well. So, for instance, would you be able to identify a delta connection or a Y connection if it wasn't specifically drawn for you in the triangle or Y shape? What I mean by that is, if you see a triangle, you know it's a delta connection, or if you see that Y shape, you know that it's Y, but these things are not physically in the shape of triangles and Ys. So can you see exactly why something should be a delta or Y connection based on the situation and not based on a convenient symbol you were supplied? If I showed you these, for example, would you be able to identify that they are delta or Y configurations? See how oddly shaped they are? They don't give us the simple diagrammatic representations. They're more physical in their visualization. So in this video, to illustrate all of these things, we'll use transformers as our example because it gives us a simple place to play with all sorts of options about these sorts of connections. We are including inductor symbols in our delta and Y diagrams here, which will give us visual endpoints. And speaking of visual endpoints, it's important that you understand that this is a very visual lesson. And because it's so visual, the content of what we're teaching is about visualizing, we need to be sure how we are interpreting the visual cues. So, for example, the line here isn't supposed to represent the real disposition of a real conductor. It's an ideal conductor, which is perfect. It has no resistance or shape or anything like that. It just passes electricity perfectly from one element to another. The path from one element to another can be drawn in an infinite number of ways. So you need to combine the abstract, ideal, and theoretical conceptions with the visual conceptions here. So we're kind of playing with both, visualizing and also an understanding of its ideal characteristics. And then all of those are coupled with sort of more physical dispositions that we're likely to see. So for example, I could have drawn this delta connection up here in any number of different ways. So I could have drawn it like maybe this. Or any other sort of way. Let's consider one side of a transformer configuration, and let's just call it primary in this case. So here are the three lines bringing in power to the transformer. These are the three single-phase inductors that make up the transformer. How are these inductors connected to the incoming lines? Well, we need to ask ourselves, what is the connection? So let's say for our first example here, we're going to call it a delta connection. So in our minds, a delta looks like this. How do we convert this shape into this other disposition? Now notice if you look at the delta, you see that each inductor is connected to two other inductors. And what I mean by that is A is connected to both B and C, B is connected to both A and C is connected to both A and B. And it's really easy and convenient to see this in the triangle shape, but how do we show that here? How do we go from one inductor connecting it to both the other inductors using the three lines in this schematic over here? So it should seem pretty obvious, but we see that there are two connection points in each of our inductors here. So one of those connection points should be dedicated to its connection to the appropriate matching incoming power line. So A should be connected to A at one point, and B should be connected to B at one point, and C to C. And that will leave us with one connection taken up and one connection on each of the inductors to assign to make this connection between the other inductors. Let's add the three incoming power lines to our delta diagram just to make sure that we're seeing everything appropriately visually, and we can kind of go through and mark off now the connections we've made. So A is connected uninterrupted to the A. So that means our A incoming power goes directly to our A inductor. That means this leg here, the connection is now established. Now B goes directly to the B inductor, so this leg has now been established. That connection is there. C, likewise, goes directly to the C, so that connection has been established. So now we have the three of the 6 connections made, both in our horizontal 3-line diagram here and in our actual delta configuration diagram here. So now up here we see that we need to connect A to B somehow. A needs to go over to B. So let's make the connection. A is connected now to the B line. Right there. There we go. So now that gets us from A to B. Now we see B needs to be connected to the C line. So let's connect B up down here over to the C. There we go. And lastly, C needs to get connected to the A line. Now you may stop and say, well, we already have connections at those points. But you see, what we talked about with the delta construct is there are 2 connections necessary for every single line. So we have 3 incoming power lines, but 6 total connections. So let's trace how the completed circuit runs through all of these connection points from one diagram to the other. So from the A to the B section of the delta here, we're going to see that connection in green, and let's show it now on our other diagram. We go from the inductor connection point up to the B line, which establishes our other connection with the B inductor connection point. And let's now do the leg from B to C. So this inductor connection point to that inductor connection point runs like that on the delta diagram. And on our 3-line, we start here and end here. So we can make the connection along this C line there. And finally, we'll finish up this C connection point here to the A connection point here. We'll make that in blue, so that little leg starts here, it's the C inductor connection point, and finishes at the A inductor connection point. And we see that it travels along the A line. So now let's visualize the completed circuit that we see, which is unique to a delta connection. We see that if we begin with A, we can continue over to B, which B then goes into C, and C returns us back to A. Circuit completed. We can follow that exactly here in our other diagram. We start here, we move back up and around, A goes to B, B goes to C, and C returns back up to A. Completed an unbroken circuit, which is unique to the delta. We won't see this exactly with our Y diagrams. And now let's take a look at a Y example. We showed a primary side delta connection for a transformer in the previous example. Now let's look at what the Y example is. So here are 3 incoming lines providing power to our inductors, and we're going to have, just like the delta example, we are going to have 3 single-phase inductors that we're going to have on our transformer. And we ask ourselves, how are these connected? And we ask the same question. What is the way we are connecting them? We're doing a Y connection. So let's talk about the unique things about a Y connection and how it will affect what it is we're working through here. So this now visually, after we worked with the delta, should seem actually really kind of painfully obvious. The A incoming power line has a single connection to our A inductor. So A gets connected to A. Very simple, single connection right there. B incoming power line connected, single connection straight to the B inductor. And likewise for C. C connects straight to C. And we can see that visually with our Y really, really simply. So we've managed those connections here that we're Xing off. Now, our only other point of connection is this middle point right here. What exactly are we going to do here? One of the great strengths of the Y connection is the simplicity with which it can employ a neutral conductor. And that's what we're going to see. We're going to see now the neutral come into play. So let's draw our neutral line up here. So actually we have a 4th line, Very different from the delta connection. We have now, instead of 3, we've got 4. That neutral now is established as the center connecting point in the Y, and we see that it, at that center point, branches out into the 3 unique inductors. So it should be obvious visually seeing this that each of the inductors have to have a direct and immediate connection to the neutral. So very simply, we make that connection appear here. So now we have 6 total connections and 4 lines. So now let's illustrate our flow of connections. We'll start out now on the A line, the line that's bringing in power, and we'll bring it all the way to our, essentially to our neutral connection, that central connection in the Y that we see visually here. How does that look in our 3-line, well now 4-line diagram? We go here, makes the connection to the A inductor, which is then connected to the neutral. The B connection, starting out in our B line, we can show here, and that comes in, crosses the B inductor, and connects to the neutral. So let's follow it here on this other diagram. We start here. It makes the connection to the B inductor, and just like before, we see it gets connected up to the neutral. And now we do the same for C. Once again, following the same path from the incoming power line to the C inductor to the neutral. And it's completed. What you can see here, a distinguishing characteristic of the Y, is we can't use that yellow tracing like we did in the delta to form that complete circuit. These lines just go out. And so there's another distinguishing characteristic you can see here in the way that it's connected versus the way the delta is connected. So notice now with the neutral connections how we have 3 connections, 3 lines coming in and joining in 1 on the neutral. We'll demonstrate that here with this yellow box shown there. That is this connection here. Though this is seemingly a very basic set of concepts, it hits on a way of understanding connections that is not necessarily easy to see. Perhaps the simplistic triangle and Y shapes commonly seen on diagrams have led to blind spots of assumptions held by engineers. A successful PE test taker will have this level of visualization and understanding, not just of simple deltas and Ys, but of the physical realities behind the diagrammed connections. Full-length Power PE style practice exams now available for purchase online.